In this video, we're performing another example with MSC Nastran Optimization. Specifically, if you're performing a frequency response analysis, we want to walk through the process of imposing a design constraint on element stresses. We're using the same 1 degree of freedom spring mass system I've described a million times before. What we want to do is look at our element stresses for this spring. And I know that massless springs usually don't have a stress associated. I used an option in MSC Nastran to apply how do I describe this? Sort of a fabricated stress, if you will, that yields a quantity I can use for design purposes. So here in orange is what the stress plot looks like for our initial design. You can see that our highest stress in the spring is actually at a value of, or forcing frequency value of 3 Hertz. What I want to do is find a value for the spring that yields maximum element stress of 200 megapascals. So now let's go ahead and walk through the process. And here, the description of the model again, feel free to pause the video, glance at this. If you have any questions after this, feel free to contact me at this email address and I'll get back to you. Here's our problem statement. We're going to minimize the price of the spring. The price is dependent on the stiffness of the spring. Our design variable will be the stiffness of the spring, and our design constraint. We're going to say that the element stress for all of the forcing frequencies should never cross this upper limit of 200 megapascals. Now, let's go ahead and walk through the process of how to do this for MSC Nastran. I'm assuming you already have your BDF file that you may have created inside of Patran or some other pre-post processor. This example already has the design variable and the design objective statements already completed. What I'm going to do now is I'm going to use my web app to create the design constraint I just discussed. So let's go ahead and switch the analysis type to direct frequency response. In the list, you can go page by page looking for element stress, or you can just filter the list and find element stress here. Let's click on that one time. And then this new row is where I can configure my constraint. First, I'll supply the upper limit. The units we're working with for this example are newtons, meters, kilograms. So my design constraint is not 200 megapascals. It's actually 2E8 pascals. Again, we're dealing with newtons, meters, so our Nastran results will be in pascals, or newtons per meter squared. For our property type, we are working with P-bush, and this is P-bush 1. For our stress item code, this is where we have to refer to the MSC Nastran quick reference guide. In chapter 6, item codes, there's a section devoted to element stresses. Go to this section and look for the section for C-bush. The C-bush section will have the item codes for the stress and C-bush elements. So here I know that as the spring oscillates, this would be the X translation. So I would use an item code of 2. So let's go back to my web app and type in a value of 2 for stress item code. As for the frequency value, in my previous videos, I've detailed what the difference is between, min, max, SSQ, RSS, and AVG. And I've also discussed what leaving a blank value means. So if you have any questions regarding that, either leave me a comment below, send me an email, or refer to one of my previous videos. And now let me go ahead and inspect this real quick and make sure I've done this properly. After I've confirmed I've done this properly, let me copy the statements from the right and let me put those in my design model. And now I can perform my optimization. So let's go ahead and start MSC Nastran. And then I'll start it now. Now that my optimization is finished, we should inspect the F06 file. In the F06 file, we want to make sure that the message run terminated due to hard convergence is there. This indicates a successful analysis. Now let me look at my objective results. Here I see that my price of the spring started at a value of $10. And then at the end, I had a value of $14.78. And my spring constant went from 2,000 newtons per meter and increased to 2,900 newtons per meter. So let me go ahead and see if that aligns with my results. And yes, it does. So everything went as planned. Again, my cost of the spring went from $10 to $14.78. This is a custom objective I created with MSC Nastran. My spring stiffness went from 2,000 to 2,900 newtons per meter. Here on this graph, the orange is what the frequency response results were for my initial design. My maximum stress at a forcing frequency of 3 Hz was 700 megapascals. But now with the new stiffness value of 2,900 newtons per meter, I have a new element or maximum stress value of 200 megapascals. So I've reached my objective given the design constraint I imposed on the element stresses. With that concludes the end of this video. If you're interested in more training, I have my YouTube channel with dozens of videos, hours of training. If you want access to those web app that really makes the process simple to perform optimization, feel free to email me and I would be more than glad to give you access to this tool. With that, thank you for watching.